We have with us Sudip Jana, who will tell us about light from neutrinos and pathways to new physics. Just a brief introduction to Sudip. He is currently a postdoc at Max Planck Institute, Heidelberg. And prior to that, he did his PhD with Professor Babu, whom we just heard. So let's hear more from Sudip on pathways to new physics, connection with neutrinos, and so on. Sudip, welcome. So you can begin your talk.
Yeah, thank you very much for giving me the opportunity to present my work. Thank you, organizers. So here basically I'll talk about two aspects. As you see, light from the neutrinos and pathways to new physics. First aspect is how neutrinos interact with light. Basically, I'll focus on neutrino magnetic moment, electromagnetic properties of neutrino. And the second thing also, it has another implication, how neutrino can shed light to new physics. There are two aspects of it. I'll just briefly discuss on that. So my talk will be presented in 4 segments. It's consists like first section is theory of neutrino masses and mixing. I'll not tell detail. This already covered by Babu, I guess. And basically, if you have theory of neutrino masses and mixing, which is one of the robust evidence that neutrino oscillation requires neutrino to get mass. So there should be some neutrino mass messenger. In the second segment, I will briefly touch about how you can probe these mass messenger directly at the different frontiers, different experiments. And the third segment, I'll talk about neutrino interaction with matter, where you do not need to look for really like neutrino mass messenger. But I know standard model fermions, how neutrino behaves with standard model fermions, basically matter, up, down on electron, which is termed as NSI, or sometimes if neutrino interacts with itself, it's called neutrino self-interaction, how those are impactful and how it could lead to connect with neutrino mass generation mechanism that I will briefly sketch about. But mostly I will highlight the 4th segment, which is understanding neutrino electromagnetic properties, basically neutrino magnetic moments and how it is very closely related with neutrino mass and so on. Okay. So before going into detail, just in one slide, this is a crowded slide, but just to one background, like most of us we know, but still like neutrino oscillation, flavor oscillation have been firmly established from several experiments. In last 100 years, last 50 years, over 100 experiments has like look for this. I just listed here the main key player of different solar neutrino experiments like Homestake, SEG, atmospheric neutrinos, reactor neutrinos, accelerator neutrinos. So far what we know that like for the oscillation, it can happen only if neutrinos have non-zero mass. I should say there is consistent theory which like without neutrino mass, like standard neutrino mass generation mechanism. There are several attempts. But I'm not aware of such consistent mechanism. So neutrino needs to get mass, but we don't aware of any such mechanism which is established for this neutrino mass generation. However, what we know about that 3 mixing angles, this neutrino oscillation parameter with few %, then mass square difference we measure. But what we don't know, sign of the delta m square. For defined hierarchy, it could be delta m3 square or delta m3 square, which defines the mass ordering or the mass ordering ambiguity. And then CP phase delta is also unknown. You see, this is the mass matrix, like PMNS matrix, which connects with flavor eigenstate to mass eigenstate. So these are the goal of next decades neutrino experiments program, like to measure these angle with more precision and mass ordering ambiguity, CP phase, and also unitarity of UPMNS. Here I wrote it down. This U is assumed to be unitary because why I say that, because it's connected with this neutrino non-standard interaction. These things will be measured in the upcoming neutrino experiment program. But that will not answer our question, right? How neutrino is getting mass. Okay. So here I'll not tell much detail, which Dr. Babu already covered. Just in one slide, I'm just showing that in standard model, this is completely technically natural. Neutrino gets light mass. There are two successful like standard mechanism, which I call like by integrating out heavy state, which is seesaw mechanism, you say, or through quantum loop corrections, you get this neutrino mass. And the lowest higher dimensional operator, which you generate from LLHH, and there are several realizations. I'm not going in any detail of it, just sketching it out. Seesaw mechanism, say type 1, type 2, type 3, loop induced. I think I did not notice, but like I guess like all these classification of defined operator in radiative model has been discussed in Babu stuff. So these are the defined mechanism of neutrino mass generation. But how, like in a lab experiment, if we see something, how we can claim that this is the model for neutrino mass? This is quite hard, but like I want to give a glimpse of it, like how to look for this type of new physics, which is connected with neutrino mass generation mechanism at defined frontier. Say, in the energy frontier, so this heavy new physics, which is responsible for neutrino mass generation, it can lie at any scale, starting from GART scale to TeV or sub-TeV scale. Since collider was built, like LHC was running and like it was very popular, so people constructed neutrino mass models which can be probed at LHC. There could be different variation, but here I am sketching it out that the standard seesaw or the radiative models which require some heavy right-handed neutrino or some double charge scalar, that has been looked for at the LHC, at the sub-TeV range or the TeV range. The standard signature of type 1 seesaw, suppose say lepton number violating signature, Simpson dilepton plus dijet. If you go from type 1 seesaw to invert seesaw, it's a lepton number conserving signature, because this mu term, it's a very small parameter. So you will get some trilepton plus missing ET signature, but all these signature has been looked for, but nothing has been found so far. So that put a limit on the mixing and the heavy new physics mass parameter. Similarly, in type 2 seesaw, it requires a SU12 triplet, which requires some double charge scalar and so on. So that's also put bound around 900 GeV, but depending on defined modes, there are several works on it. And type 3 seesaw also same scenario where you require SU12 triplet fermion. There are several works on it. So far we find only this type of bound from LHC study, but then the question comes like, okay, it can appear at the LHC for sure, but like what happens if you construct neutrino mass model at the higher dimensional operator? Then what happens? In the y-axis, I am showing the new physics scale, and in the x-axis, defined dimensional operator. As you see, if you go higher and higher dimensional operator, the new physics scale can be lower and lower. Okay. So there are several neutrino experiments ongoing. So if it happens that the neutrino mass generation happening below electroweak scale, okay, so then it could happen that some of these effects could appear in low energy experiment. Here I am just, this is a kind of schematic diagram, like for Yukawa varying from 10 to the -2 to 1, you see free level say 10 to the power 14 GeV, the new physics scale you require, which you cannot see directly at the experiments. If you go to one loop, then there will be extra chiral suppression. So you are new physics can be lower and lower. Here I am just showing this neutrino mass formula, but it always doesn't hold like this way. But here I'm writing all these possible dimension operator for this dimension 5, dimension 7. You can write it down, and you see that your new physics can be light. So I'm giving one particular example, which I worked with Pedro and Renata in 2018. That one such example is like you consider some dark gauge symmetry, like you want symmetry where you consider two right-handed neutrino, one carries +1 and other carries -1 charge, so that you can cancel the triangular anomaly. Due to that, if you assign some charge of this right-handed neutrino, you cannot write down, you are not allowed to write down this Majorana mass term. Okay. So generally in inverses of what happens, like there is a mu term, particularly here, which by ad hoc we take to be KEV. There is no explanation of it. So here we try to generate it dynamically. And also the other right-handed neutrino, since carries a charge, it does talk to standard model because standard model Higgs is not charged under that. And due to this, what happens, like all these terms comes from this Yukawa. And one interesting thing is that both of these scalar gets waved via induced mechanism. S1 is responsible for U1 breaking and Higgs, the electric symmetry breaking. You see, if it is getting induced wave, this can be very light. And whenever this 1, 2, or 2, 1 entry is small, you can see that new physics scale can be much lighter and it can go below electroic scale. So this is just one realization. And as I mentioned, like if you construct such neutrino mass models, then what happens, like it will show up and low energy experiment. One interesting realization immediately we found, due to this type of setup, we found like there is a one-to-one correlation with MiniBooNE access. So this type of G prime can have kinetic mixing with photon through which it talks to atom. Basically, in case of MiniBooNE, it was CH2 molecule. Then neutrino via mixing goes to right-handed neutrino. This G prime strongly interacts with this right-handed neutrino sector. Now, if this N decays back to this G prime and neutrino, this G prime on cell, then this G prime will go back to E minus E plus pair, collimated pair. And if it is like that, you can explain this energy spectra like very well for the MiniBooNE spectrum. And this is the parameter space in the mixing and mass plane we have shown. This also work done with Pedro, Renata, and Enrico. These defined color bands are consistent with defined sigma with MiniBooNE access. And this is the experimental constraint. I'm not going in detail. After this 2018 work, there are a lot of development has been done, like people work with, come up with several explanations. Recently, MicroBooNE has also data. I'm not going into detail of it. Even if like after MicroBooNE's data as well, like electron-like event spectrum or photon-like event spectrum, still this is one of the best explanations still survives for the MiniBooNE explanation, because they did not really look for E minus E plus collimated pair spectrum. And this was the electron-like event access. Yeah, I'm not going on detail, just want to sketch it out. Then you can ask, like there will be several constraints on that, how we are satisfying in this low scale. This is true. There is a nice paper by the Gubia and Kovac company.
So
like
just a quick question here,
yeah.
A comment rather. MicroBooNE has no effect on your studies?
No,
The previous slide, if you go.
Yeah. So MicroBooNE look for particularly electron-like events, just a single electron.
Yeah.
And as far as I understand, like they put a nice box in there when they presented their results. They particularly mentioned that this E minus E plus this collimated pair spectrum, they need to they do not have technology, or they did not look for it particularly. So they need to look for it. This will look completely different than the standard electron-like event searches or photon-like event searches. That's my understanding.
I see. But there was a paper by Peter Denton which said that if there is only coupling in the electron sector, then sterile neutrino is allowed. And what would be the implication of?
Yeah, so no, it's E minus E plus pair. It's completely defined kind of spectrum it will give. Okay, let me show you. So what you are saying, basically, if you have fourth sterile neutrino oscillations, which is after LSND, people are considering those type of effects, like, okay, maybe it's basically this diagram. If you see, you are producing mu bar and then you are getting electron-like events. Generally, the standard explanation is like, okay, if you consider some fourth sterile neutrino, which is lies in the EV scale, like which is affecting this kind of phenomena, and there you look for a single electron-like event. You see, like if you have some fourth state and then goes back to electron, pure single electron type of event, here actually I have not shown, like if it is electron-like, the spectrum will be a little bit different than the fuzziness of the like 2E minus E plus spectrum.
I see.
And it's okay. It's a standard way, like it's a 4.7 sigma tension between appearance and disappearance data set under EV sterile neutrino interpretation, and also this cosmological bounds further thread this EV sterile neutrino hypothesis. But as you mentioned, there are several loophole people are coming with, like how to survive this fourth sterile neutrino. Yeah, I'm not going into detail, just a main sketching part of it, like all these neutrino mass messenger, how you can look for neutrino experiments. So similarly, I just gave one example, but there are several possibilities it can happen whenever you are constructing neutrino mass model at that low scale. It can appear with neutrino magnetic moment, some dark trident signature or trident signature. Decoherence, non-unitarity, there could be several effects. Okay, so it's very challenging, but it's not impossible that to construct this type of theory. It can happen, it can lie at any scale, or it can lie at heavy scale also, which we cannot see. Later I'll come to that fact, like how there is one-to-one correspondence between this neutrino mass mechanism and magnetic moment. So here just I want to conclude with this section by saying that there are interesting aspects now, like phenomenologically, since several neutrino experiments are ongoing, LIC experiments are ongoing. So in different frontiers, you can look for different type of effect of this neutrino mass. But it will be very hard. That's my personal opinion. But like it will be very hard if we see something also. We cannot like it will take like several models can come up with same explanation. So for that, you need some neutrino properties which could pinpoint particularly which kind of mechanism it is. Okay, now I will briefly talk about how neutrino interacts with our known matter. We know neutrinos, we know up-down electron, how it talks to the matters, and how it talks with itself, because this type of effects will, like from astrophysics, cosmology, as well as in a lab-based experiment also, it will impact. Okay, before going into detail of neutrino non-standard interaction, I think that also partly mentioned by Babu. I will discuss the complementary part. So since there are different kind of audience, so like most of us, we know neutrino standard interaction, but still I am sketching it out that what is, before going to non-standard interaction, what is standard interaction? Standard interaction, I show these two diagram in standard model, to W exchange and the G boson exchange. There is something special in the left diagram. If you see this W coupling is flavor diagonal, this mu E, you cannot change the flavor nu mu or nu tau. Because if you are considering matter interaction, then it should be nu E. But for the right diagram, it's a this coupling is flavor universal, because you can switch with nu E to nu E by nu mu to nu mu and so on. And due to that, one interesting fact is that coherent forward scattering of mu E of electron in matter generates a matter potential. So this I'm writing this potential like which is 10 to the power minus 12 electron volt in solar core, which seems very small, but if you multiply by 2 times energy times of, and then this potential, and energy is roughly say 10 MeV in the solar core, then you will see that that's exactly delta m square 10 to the power minus 4 EV square. So this modifies the reflective index of nu E. These are pointed out by Wolfenstein, Mikhail, and Spino in old age. So this is neutrino standard interaction. On top of this, if there is some beyond standard, some extra interaction, if we found neutrino with matter, which we termed as neutrino non-standard interaction. Okay, and quite often, whenever you are trying to construct neutrino mass models, it's more likely that you will generate NSI, but it's in a different strength. So it's quite important to study this type of operator, or the like here I just write it down. You can write the NSI operator at different like different dimension, but the Wolfenstein version of it in 1978 like as you see, this is the operator. You can write down neutrino, how it's talk with matter and matter. Like this epsilon is the strength of the NSI, charge current and neutral current NSI. You can write it down in terms of this type. Just I want to here mention one point that this type of operator has been studied, the NSI strength has been studied for different kind of neutrino experiment. But however, to realize such effect or if it impacts really, suppose a T2 nova discrepancy, just I'm giving one example, you can explain with some large NSI, but this type of realization of this large NSI is quite challenging. It suffers with charge electron flavor violation. And also at the end of the day, if you realize some kind of NSI also, you need to realize from which setup or from which theory you can come up with this type of NSI strength, which is quite challenging. So UV completion of model which can yield such NSI has less studied. Okay, so yeah, I'll also refer this to Babu's talk, different radiative model, but since I'm talking about some different aspects, so just briefly sketch about, in our paper, we nicely categorize whole class of radiative models. No matter what type of model you write down, you can categorize in two categories based on NSI. What is that? We called it in our paper type 1 radiative mechanism. When there is at least a standard model particle inside the loop, what happened? You can obtain from, I think this type of operator Babu already mentioned, you can obtain from different dimensional operators to make this delta L equals to two selection rule. And you can write down all these operators very classified way. And there are limited possibility of it. It's not infinite possibility. Okay. And this has been pointed out by Babu Leung in 2001. Then I think in that paper, they missed one operator, all singlet operator. Then the Gubia and Jenkins in 2008, they wrote another paper and they complete the full picture of this operator. In this type of model, or in this type of mechanism where you have this type of like at least a standard model particle inside the loop, and when you can write down this type of operator, you generate NSI at certain strength. Okay, cut down this diagram and you can get this type of operator. However, there is a other version of it, which is type 2 radiative mechanism, where there is no standard model particle inside the loop, and you cannot generate such diagram. And if all the particles are like BSM particles, then you really like there are infinite possibility you can come up with. Okay. But the main distinction is that if some sort of, there is nothing good or bad, just these are the two classifications. So one such example is much photogenic model. These models predict negligible NSI. So the main distinction will be, if I try to look for some broader picture, if some NSI is realized, these type of models are not good or doesn't qualify for NSI. Okay. So this is the just classification, and also I will quickly go over it. I think Babu already mentioned. Then we systematically study this class of model, basically type 1 class of model, which generates the NSI. And I previously mentioned one comment that that it suffers from charge electron flavor violation. There are some certain trick of it. Just I am showing one particular model, it's a G model. You get the neutrino mass at radiatively. You see here there is chiral suppression as well as loop suppression. Although you neutrino mass you get at the loop level, you get the NSI at the tree level, but you can see L nu charge scalar, and then you just flip it back, then you can generate the NSI operator. But the main trick is that if it is a SU12 singlet, this matrix is antisymmetric in nature. There are two types of Yukawa going there, but the other Yukawa is completely free. And as you see, if you go along the row of the matrix, it's the charge electron flavor changes. So as long as you are not populating two entry along the row, a large entry, it cannot suffer from large electron flavor violation. So you can populate along the column large entry, and which is responsible. So suppose a first column, where neutrino change the flavor along the column, and the first column is responsible for this all these NSI. So you need to play with electron flavor violation. You can play this game, and how to satisfy with this constant you can come up with. And that's the just I was to mention, like how to satisfy in charge electron pair violation and neutrino observables. You can still satisfy some correct strength NS or like large strength NSI. I'm not going detail of the model, maybe Babu already mentioned. So also there will be several constant and so on. I'm just highlighting. You can get some all the diagonal NSI maybe in large strength and so on. So anyway, this is kind of a summary plot I'm showing, like defined 6 type of NSI in defined class of radiative model. You can categorize in as a like, I think here we categorize in 4-6 category, and you see like what are the maximum NSI you can achieve after defined kind of constants, say electroacquisition constant, LAC constant, or left constant, charge breaking minimum. Different kind of constant has been considered. I'm not going in detail of it. Okay, one interesting implication we found that like IceCube, ultra high energy neutrinos, due to if you have such a charge scalar or something which is responsible for the radiative mechanism, in general you require some sort of charge scalar in general, like it can be defined kind of variation of model. But if you have such charge scalar, one interesting effect we found in IceCube, you see in the standard model, you can look for Glasso type of resonance, which will occur at 6.3 PeV. And this is the things you can see in the IceCube spectrum. If you have such, suppose this type of radiative mechanism realized at the light scale, where charge scalar lies in the 100 GeVs, so then it could happen that you can see some Glasso-like resonance, and side by side beam, it could happen. And we look for that, and for a suppose for example a 100 GeV, you can see this type of peak at 9.3 P. In future, if you see that, like this will be a good indication for this type of radiative model. And based on that, we put a like sensitivity for the NSI. This is a defined kind of NSI search because there is standard as IceCube atmospheric searches. But looking at resonance searches, it could probe a large parameter space. And you can see it could be also like complementary to LAC and other experiment also. So it's very interesting. Although you see this IceCube 50T node, these are 2,635 days, you may say that, oh, this is too long time, like if you multiply by it. So, but it is not like that. So it's we did for IceCube, but if you go to IceCube Gen 2, the volume will be upgraded. So I think it will be around 10 times or so. So basically, it's 5 years of operation you require to realize this type of thing. Okay, so then I quickly mentioned that in energy frontier, this type of NSI operator you can probe at the LAC as well. And there are several studies by Alexei, Friedland, Jan Shoemaker and company in 2011. Then Devjyoti, Kirtiman, Saurabh, they did also in 2018, and we did it in 2020. There are several defined aspects has been discussed in different papers. There are maybe other studies also, like I'm not putting all these papers. But the basic idea is that there is a long history of dark matter searches, mono X searches. And several studies has been done. These mono jet searches, if you radiate gluon from the initial state quarks, then you can look for, from these operators, you can look for missing ET plus mono jet searches, right? So this is not like the other golden channel searches, like where you can really look for invariant mass spectra, like left one. It's rather like other way around. It has background huge, but small enhancement in the tail of the missing ET distribution. From there, you try to look for dark matter. Same story applied here, like just replace dark matter by neutrino. That basically the NSI operator. Okay, that's basically the NSI operator which you could look for by looking at PP2 missing ET plus mono X, but mono jet missing ET plus mono jet is the most promising searches. And then we look for it. For that, what we have done, like we implement a simplified model of NSI where G prime has quark and the neutrino couplings. You can write down the NSI strength. Then you can look for Okay, there are neutrino experiments, different bounds as you see in different dashed color. What LHC can say about it? We look for it, and we found that if you vary the G prime masses after a certain point, where basically this EFT regime is valid, like EFT regime is for the LHC when the mass of the mediator is much above the scale of the processing point. But one interesting fact is here that although we treat if we treat like this type of EFT of NSI at the LHC at some, but this is inconsistent. This is coming from simple inequality relation that a G prime, suppose say you consider which has quark-quark coupling, neutrino-neutrino coupling. So just demand that the total width of G prime, so at least it will go to QQ prime or like and neutrino-neutrino. Just claim that this G prime's total decay width should be larger than the partial width of quarks and neutrino. That translates to the inequality, this condition of the NSI, and you see, although you put constant on the NSI, but that is inconsistent from the theoretical point of view. So you really look for then, but also like whenever you try to construct UV complete model, you will see that some perturbativity constant or other things is killing this type of EFT treatment. At least we are not aware of such complicated model, like in simple or minimal UV completion, you cannot find this type of validation. And these light blue color is for HLLAC with we consider some simple 1% and 3% systematic uncertainty for that. Okay, I'll not go too much detail of these, but just want to mention that there are very nice complementarity between this LHC and neutrino experiment. That LHC sensitivity displays a strong dependence on the mediator mass. It depends on the mediator mass, but it's free of parameter degeneracy. But neutrino oscillation measurement, they have degeneracy, but no mediator dependence. And like neutrino oscillations are not sensitive to axial interaction, but LHC data is sensitive to both vector and axial new physics contributions. These are nice complementarity. All these features show the synergies between oscillation measurement and collider data and probing new physics in the neutrino sector. Also, it can remove this degeneracy, as I mentioned. This is in the Dirac CP page and defined NSI. Also, these are, if you have two NSI simultaneously present, so it can break this degeneracy. And as I mentioned, if you go to a particular UV complete model, you will face some more phenomenological consequences. Whenever you try to achieve some NSI, and you see just for a particular example, we consider U1 B minus L, like when third family is gauged. So there are some BB bar tau tau constant or some other low energy observable that supersedes the constant from monojet study. In some of the parameter space, it might be relevant, but it's a very narrow. And like if you go to higher and higher mass, you need to have some gauge coupling. Suppose say whenever you are considering NSI for heavy mediator mass, then you require some gauge coupling, which is in perturbativity. So like you need to be consistent. And these are defined constant. Okay, so up to this, like I talked about all these kind of different approach you can take to probe this type of neutrino mass models, either by looking at direct mass messenger or looking at like different kind of effects through how neutrino interacts with matter. Now I'll talk about neutrino's electromagnetic property, which is very closely connected with neutrino mass generation mechanism. It's not like the other scenario where you cannot pinpoint the mechanism. There could be several, like multiple options can arise. Okay, before going into detail, we are quite aware of charge electromagnetic moment. Neutrino basically chargeless up to our understanding. So there is some basic difference. How we measure, we quite often talk about muon magnetic moment, electron magnetic moment. What we exactly measure? It's, you can think of a like racing cars in a track, right? So in muon G -2, for example, what they are doing, thousands of muon jeeps are like circulating around a 50-foot circular magnet. And what you measure, actually, how much do they rotate on their axis in a powerful magnetic field. as they race around the magnet. And you basically punching this muon beam, and after a loop, like then again you punch a muon beam. So it's the measurement. It's the way you measure the muon magnetic moment. Suppose these are charged particles. But what about neutrino magnetic moment? It's a charge, like it has no charge. So how, like if you have some magnetic moment, its measurement procedure is little bit different. Just to one-to-one comparison, I just give one example. Neutrino source can be different. Say it can be solar, it can be some other neutrino sources, accelerator or something. But here I'm just giving one example. Suppose a solar neutrino is coming and reaching Earth, and in the Earth detector, if you have this type of neutrino magnetic moment operator, as I said, light from the neutrino, they basically photon. How if it emits, this photon will talk to matter. And from there, looking at electron recoil in scattering experiment or nuclear recoil, you basically measure this neutrino magnetic moment strength. And so then I'll tell a little bit like in one slide, just history of it. Like this quest for neutrino magnetic moment was started even before the discovery of neutrino. Cowan, Rennes, and Harrison in 1954, and yeah, this is the first paper which appeared on neutrino magnetic moment. They put from the reactor neutrinos, they put a limit of neutrino magnetic moment 10 to the power -7 Boltzmann, and it's a very important property which they yeah, I found this paper is the first paper which appeared in the literature on neutrino magnetic moment, and later Rennes got Nobel in 1995. So after this Cowan, Rennes, and Harrison limit, there are several experiments look for this type of neutrino magnetic moment, and this becomes very popular topic in late 80s or start of early 90s, because due to some sunspot activity, people have shown the solar puzzles, people are excited about, and then there are a lot of activities. So reactor-based experiment, I put it all this chronologically. This Cowan, Rennes, Harrison limit was improved to 10 to the power -10 Bohr magnetron, say Rubnu, Mono, Texano, Gamma. In actually 4 days ago, Konas in Max Planck, like they look for also this neutrino magnetic moment, and they set a limit of 10 to the power -11 Bohr magnetron. Then accelerator-based experiment and solar neutrino experiments, say Borexino and Jana, and you aware of that Jana also see something in a low energy like excess between 1 to 7 keV, and which is consistent with neutrino magnetic moment 1.4 to 2.9 times 10 to the power -11 Bohr magnetron, which is quite exciting. Whether it is due to neutrino magnetic moment or not, but its importance never will be dropped down. It's a 1-to-1 relation with neutrino mass that makes it important. Now let's see what are the other consequences of this type of neutrino magnetic moment operator.
Sudip, just to let you know that I think some 7 minutes are remaining, so that you can tune your talk accordingly. Yeah, thanks.
Okay, yeah. Yeah, I'll be done probably. So you see that this neutrino magnetic moment current experimental sensitivity around 10 to the power -11 Bohr magnet. Then you may ask, like, there are strong astrophysical constant and so on, like how to deal with that, and what kind of constant comes from astrophysics and cosmology. And that is true, completely true. If you have like this kind of photon talks to neutrino, what happens? Photons in the plasma background, it gets some plasmon mass, okay? So few tens keV or so. So then it can decay back to 2 neutrinos. Due to this extra drainage of energy, it will be in conflict with standard solar evolution model. And from that, you can set a limit on from this globular cluster, you can put a limit on neutrino magnetic moment, which is 10 to the -12 Bohr magnet. Raphael and company in like they derive this limit. And there are also cosmological limits from Big Bang nucleosynthesis and so on, which is 10 to the -10 Bohr magnetron, which is not so stringent like the astrophysical. Then with Babu and Manfred in 2020, we proposed a mechanism which we call neutrino trapping mechanism. If a neutrino talks to some ultralight particles, so or like neutrino can develop also medium dependent mass in say in this type of stars environment. Suppose a neutrino develops some few 10 keV mass, and if you do not allow this plasmon to decay back kinematically to 2 neutrinos, then this type of bounds are not directly up. And these medium dependent mass you can get from these like ultralight particles interaction with these neutrinos. And for that, we closely follow all theoretical evolution of the medium dependent mass of the neutrino. And also there are recent paper like which you need to be very careful about fifth force constant, astrophysics and cosmology. Recently, Smirnov, Alexei and Babu et al. Like they have studied in different aspects, but this neutrino trapping mechanism we propose, which can be which can evade this type of astrophysical bound. If neutrino is trapped, then this type of bound are not applicable. Now let's see what is the main problem of what is popularly known as neutrino magnetic moment mass conundrum. If you see this operator, neutrino, neutrino, and photon, and like you see both are chirality flipping, same helicity flipping operator, neutrino mass and neutrino magnetic moment operator. If you remove the photon, you will end up in neutrino mass. Okay. So I showed a cartoon diagram. This is experimental sensitivity. If you try to achieve neutrino magnetic moment, actually you will pull out the light neutrino mass at the heavy scale. What does that mean? From this one-to-one dimensional argument, you can write down neutrino mass in terms of neutrino magnetic moment. Okay, where M is supposed a new physics involved. Now, neutrino is chargeless particle. You require some charge particle at least, and you know, like a lab-based experiment cannot go below 100 GeV, some charge particle which is in conflict with some. There will be some tight constant and so on. Even if with that kind of naive estimation, you can see that light neutrino mass requires to achieve 10⁻⁻11 Bohr magneton, you requires MEV size, and which is in conflict because you know that it should be sub EV scale or EV or like 0.1 EV and so on, Catherine experiment. So basically, in the absence of additional symmetry, electronic symmetry, or without severe fine tuning, one would expect neutrino mass several orders of magnitude larger than the measured value. This is typically known as the neutrino mass magnetic moment conundrum. As I earlier mentioned, it was well recognized 3 decades ago when there was great interest in explaining the apparent time variation of solar neutrino flux detected by the chlorine experiment in anti-correlation with sunspot activity. Such a time variation could be explained if the neutrino has 10⁻⁻10 Bohr magneton, which would lead to spin flip transition inside the solar magnet. It's pointed out by several people. Lim Marciano in 88, Evgeny in 1988, and late 80s and early 90s, there are significant theoretical activities dependent on this kind of solar spot activity. But unfortunately, after that, no significant theoretical development has been done. Taking neutrino magnetic moment and phenomenological study has been done, but how to realize and to solve this neutrino mass problem, but there is no further interesting development has been done. And it's becomes very interesting or relevant today if we in this type of upcoming, as we see in Jana, we are seeing something which is consistent with neutrino magnetic moment, as well as like in upcoming days, if something shows up, so that will be clear indication of this, like some neutrino mass mechanism it will pinpoint towards. So let's briefly sketch out. First, I should say neutrino magnetic moment. What are the prediction dependent on the mechanism? How you can say that? Okay, let's see. So in the standard model, neutrino mass is exactly 0. Neutrino magnetic moment is exactly 0. Okay, you are not generating neutrino magnetic. It's not like charge lepton magnetic moment. You generate some particular strength. Neutrino magnetic moment is exactly 0. As long as you are not generating neutrino mass. Whenever you are generating neutrino mass, you are generating neutrino magnetic moment at certain strength. The simplest example, you can say that, okay, this is the model, like just a right-handed neutrino extension, standard model plus right-handed neutrino. Then you can draw such a diagram through W boson exchange and where this mass insertion happening outside the loop. Then the whole diagram, neutrino magnetic moment, becomes proportional to this neutrino mass insertion, okay? And if you set the maximum scale of this mass of neutrino 0.1 eV, you can see that you can maximum achieve 10⁻⁻20 Bohr magnet in this type of setup, which is computed by Fujikawa and Strock in 80s. I will talk about the other paper, what is the importance of this Bell et al. Paper, why I put it, I'll tell in detail just after this slide. And then left-right symmetric model. Okay, then you can say, what about if I come up with some loop where I can replace the neutrino mass insertion in the loop rather than charge lepton mass insertion? Then I'll get some enhancement. This is true, but for that you require some new gauge bosons or right-handed interaction, so that you can connect newer to newer gamma. So, but this type of also this doesn't help. The reason is that you need to go through WLWR mixing, which is constant by muon decay asymmetry parameter or B2S gamma decay. This is also pointed by this computed by Japan in 1999 and student in King and a review in 2014. And you can maximum achieve putting simple argument, like you can see that like 10 to the minus 15 Bohr magneton. I'm not going in detail of the other scenario as well, like supersymmetric theory, you can R parity validity, Suji also same thing, same arguments applies, like you can maximum achieve 10 to the minus 15 Bohr magneton or so on. So then you can ask like what happened to our favorite seesaw models, the Majorana scenario. So what happens? There is much more suppression. The scenario is much more worse because if you see the neutrino magnetic moment 3×3 matrix, it's an anti-symmetric matrix for the Majorana transition type of magnetic moment. Then you do not have diagonal entry. In that case, it is much more suppressed. It's like you can, it's like 10 to the minus 23 Bohr magneton, which is computed by Paul and Wolfenstein in 82. So the conclusion is clearly these values are well below the sensitivity of the current experiment. So then I earlier just mentioned Bell et al. Paper of 2005. I just quoted it like what is the importance? Suppose say currently if we realize or if we discover neutrino magnetic moment in case at the current sensitivity level, one can claim that based on this naturalness argument that it must be Majorana in nature. It cannot be Dirac. This in this PRL paper nicely they have pointed it out that if you say write down the effective operator of Dirac, like you consider a right-handed neutrino and write down those operators, because you need to get neutrino magnetic moment coupling would be generated by gauge NPGN dimension 6 operator that couples the matter field of SU12 and U1Y gauge fields like this. And the using the same operator, you generate L nu R say phi phi phi, like this is the like in the dimension 6 you can get the neutrino mass, same neutrino magnetic moment operator in Dirac scenario. It generates the neutrino mass as well. I'm not going in detail because I have less time, but the main point is that Dirac neutrino magnetic moment beyond 10 to the power minus 15 or 14 Bohr magneton is unnatural. That is the whole story of the paper. And for Majorana scenario, this is not the case. And the basic difference is coming from the this flavor symmetric scenario. If you write down those operators, the basic neutrino magnetic moment operator must be generated by gauge invariant operator involving S equal U1Y. That comes from dimension 7 operator. You can see utilizing that same operator, you can construct LLHH. So this same neutrino magnetic moment operator contributing to the neutrino mass, but they computed it. As I said, due to this anti-symmetric nature, this limit is much more natural, like 10 to the minus 7 Bohr magneton or so on. From this argument, you can claim that, like if this is just a active neutrino magnetic moments, if it is realized, it should be, it most likely, better to say most likely to be Majorana in nature. Then I will in 2 slides just I will tell what is our finding, like how to solve this neutrino mass magnetic moment conundrum. These are 2 independent mechanisms. We systematically investigate and we find 2 independent mechanisms which can solve this issue. Like without neutrino mass contribution, like consistent with neutrino mass based on some symmetry, how you can get that. The first one is spin symmetry mechanism. Suppose say like what is the main like story of it, that if you have in renormalizable gauge theory, there are no direct coupling of the type gamma, W, and S. The scalar is spin 0 particle, spin 1 particle, and gamma. If you remove the photon, you cannot come up with neutrino mass. So what I try to mean, like for the contribution of neutrino mass, it is well known that for transversely polarized vector boson, the transition from spin 1 to spin 0 cannot occur. Only the longitudinal mode or the Goldstone mode would contribute to such transition. So that means you can generate neutrino magnetic moment large, but neutrino mass you are not contributing from the same diagram. This spin symmetry mechanism, this type of graph you I think you are aware of for in terms of muon G minus 2, quite often popularly known as bar G graph. For neutrino magnetic moment also, Barfree and G in 1990, they pointed out this type of diagram can lead to large neutrino magnetic moment without conflicting with neutrino mass. The same story, but it was never been computed. Okay, so but they come up with like G model extended with multiple scalar extension. Then in 92, one comment paper, Babu et al. They pointed out that it can be realized in simple G model. But it was never computed. But we find that that is in conflict. Like if you consider all these loop corrections, you will see that you need to be consistent with lepton-hadron universality, and also suppose say this type of cubic coupling. You cannot take it to be large because there are two Higgs insertion is there. So there is a proportionality of electroid wave.
Can we conclude? Can you please conclude?
Okay, sure. Maybe in the next slide I'll conclude. So from that, what will happen? Like you cannot take this type of cubic coupling much large. That will constrain you to say that it can be maximum 10 to the power minus 12 Bohr magnitude. And this is the last possibility, which we consider to be horizontal symmetry. Although the two operators which I said that both are same chirality flipping, but there is some difference in the Lorentz structure. The mass operator being a Lorentz scalar is symmetric, and whereas the magnetic moment is anti-symmetric. In 88, Holocene proposed this SU2 nu symmetry, where nu transform to nu C under this, that can generate the neutrino magnetic moment. That later pointed out by Barbary and Mohapatra in 89 that this is hard to implement because this doesn't commute with standard model. This doesn't respect the standard model Yukawa. So then, so this is just the realization. This is maybe I'll finish with these slides and so on. So we propose along the flavor, like we said that a horizontal symmetry acting on the electron and muon families can serve the same purpose. Simplification is that this SU2 horizontal symmetry is approximate and broken explicitly by electron and muon mass. This is analogous to the chiral symmetry breaking in the strong interaction sector by mass of the light quartz. And as you see, there is no extra standard model fermion. This is just defined represent like in SU2H, what are the charges? The fermion spectrum is exactly same as standard model. There are some scalar extension, and this SU2H acts horizontally and SU2L acts vertically. Okay, I'll just skip that. So due to that, you will get basically two diagram for neutrino mass exactly cancels out and the neutrino magnetic moments add up. So you can get that. And this is a summary plot. As you see, this neutrino magnetic moment in defined models, this current sensitivity of the experiments lies here. If you see in next, like in upcoming experiments in this 4 order of magnitude, if you realize something, there is no model can successfully mechanism, like you need to have to align with some type of leptonic symmetry, otherwise it's impossible to achieve this type of neutrino magnetic. Yeah, sorry, I have no time to explain that. We also find an interesting possibility that neutrino magnetic moment and charged lepton magnetic moments can be correlated, and we found that it's okay. Anyway, so this is the summary. So we need to look for in defined frontier different type of possibility to pinpoint the neutrino mass mechanism. And thank you.
So thank you very much, Sudip, for this very nice talk. Now I would like to invite questions. I don't see any raised hands. Does anyone have a question? While people think, maybe I can ask a question. When people talked about spin flavor precision, of course, when there is a non-zero magnetic moment, that possibility exists. But the fact that neutrino oscillation experiments are have kind of ruled out this possibility, does it have strong bearing on what would you like to say about it? I mean, what is the implication on the neutrino magnetic moment coming from not seeing spin flavor precision in neutrino experiments?
Like you are saying, spin flavor. Could you please explain it more? Like what are the bounds you are talking about?
No, so initially when solar anomaly was came to light, there was this possibility, assuming that neutrinos can change spin. right?
Yeah.
So, so that was one of the likely possibility of neutrino flavor changing and some
Yeah.
deficit being seen. But now that is consistently ruled out, right?
Yeah,
From the
that's the
oscillation experiments.
yeah, exactly.
What would be a serious comment to make from there to say something about the neutrino magnetic moment? Can we say
Yeah,
something
so
conclusive?
yeah, that's the thing. So that strength is 10 to the power minus 10 Bohr magneton, which is not sensitive as this what you are saying. Yes, like during this late 80s when these things comes, and this possibility was ruled out by 10 to the power minus 10 Bohr magneton. But now I'm talking about 10 to the power minus 11 Bohr magneton or 10 to the power minus 12 Bohr magneton, which is far away from this which is
Regime.
the sweet spot of current scattering experiment. Yeah.
Ah, I see. So that is something which was, I mean, this regime was not
Yeah.
probed there. I see.
Yeah.
Okay. So if one doesn't see anything in these current set of experiments, then neutrino magnetic moment that in that band is not going to be there. I mean, its value will be somewhere different from there, right?
Yeah. My comment will be like this. So if we do not see neutrino magnetic moment, my impression is that working on this neutrino mass models, there is neutrino magnetic moment as long as you are generating neutrino mass.
Sure.
It will be a
It
different
should
strength.
generate, yes.
It should generate. Now, one interesting possibility we are looking forward for it, like next galactic supernova. In generally lab-based experiment, due to this, energy threshold of this electron, they look for. You can ask the same question: why we look for electron recoil rather than nuclear recoil? The reason is that neutrino magnetic moment goes like 1/T. If you see the differential cross section, if you go to lower energy recoil, then you get the bump, and from there you see this axis. But due to some realistic scenario or this threshold effect, you cannot go much beyond. At least I do not know any experiments which go projecting sensitivity beyond 10 to the power minus 12. But one scenario could happen that next galactic supernova or so on, which we are finalizing it, where in addition to the MSW resonance, where you have spin flavor resonance, and we are taking some realistic assumption where we are looking for dune and hyper Kamiokande, and we are seeing that it will put constant on new magnetic moment times the magnetic field strength of the supernova. But say for 10 to the power 10 Gauss, we don't know that, but the main point is that it can be as sensitive as say 10 to the power minus 15 or 14 Bohr magneton. That much sensitivity we can go up to.
But it will crucially depend on the conditions, on the magnetic field and so on.
Yeah, exactly. Yeah, you are right. It will crucially depends on the condition. Suppose say for dune case, here actually measurements is little bit different. The other cases, like you look through the scattering, but in this case, you look for the energy spectrum, because whenever you have transition magnetic moment, nu change to some different flavor. So what you expect in the flux, you should distort from there. From there, you can reinterpret of the neutrino magnetic moment. But it's depend on the solely on the condition and the flux uncertainty, as well as the magnetic field strength and the distance also. Yeah.
Yeah. So are there any questions? If somebody cannot speak, then please type in the chat box. Perhaps none. So maybe it's time to thank you again, Sudip. And I would like to hand over to the organizers, Manimala.
Hi. Yeah, so the morning session ends here. And thank you, Sudip, Professor Babu, and Poonam. Yeah, so I think we will again resume in the afternoon at 2 p.m. Okay, thank you all.
Okay, yeah.
Thank you very much. Yeah.
Thanks.